This is a question for Ross. IOCGs and pyrite.
Sorry, mate, where are you?
Yeah.
Oh, right.
IOCG.
Oh, yeah, generally, what with the pyrites we've looked at from IOCGs tend to be very cobalt rich, which is common for high temperature pyrites, that they can be a lot more cobalt rich. But other than that, I don't really know much about them. They tend to be zoned and fairly complex. But yeah, there's fair room for study. In fact, there's another project that CODE's going on looking at that very aspect in some IOCGs in Queensland. It's a joint project with the Queensland Geological Survey. Jeff Steadman's involved in that.
Yeah, question for Aisha. What is the vanadium relationship in your chlorides?
Yeah, so vanadium is one that, at least at Batu Hijau, decreases with distance from the deposit center, similar to titanium. It really depends on things like intrusion geometry. Host rock does play a role in the compositions as well. But yes, vanadium over nickel is actually one of the proximeter ratios that are used to calculate a proximeter equation.
And my question is for Steve. How did you arrive at the list of elements to discriminate the different fertile from barren, other than it was working for the systems that you knew to be fertile? It was not an unusual list of elements, but not the first that would spring to mind.
Yeah, we looked at it first from an analytical perspective. So we said those elements, we started with 48, and we winnowed it down, and basically you could just see elements that consistently were below detection limit in certain deposit types, certain types of rocks, certain types of carbonatites. We eliminated those because we wouldn't be able to use the technique across the entire spectrum of data that we had. And then we also looked at deposit types in general. So certain deposits we wanted to look at barium because that occurred in a variety of deposits, and there were other applications for those elements to use. So if you were a carbonatite specialist, there's certain elements you want to use because there's a whole raft of things you can do petrogenetically. So some of those we wanted to include in the database, but largely it was analytical. So were those elements in abundance in all rock types, all deposit types? And those 11 were the best. We looked at a couple others. You could switch a few in or out. That DPA technique is extremely robust because multivariate. So you could actually, we went down, I think we got to about 6 elements that we specifically made them not compatible, and you will still get the same classification despite the fact if they're below detection limit or above.
But there were some metals. There weren't very many ore metals, were there?
Like, I think there was lead in there, but there was not copper or zinc or just.
Yeah, because those aren't going to occur, say, in a diorite or in a barren intrusion. So we didn't need those. Those actual elements weren't useful for that particular study. If you were just going to look at ore deposits, you could probably include those in. Mm-hmm. But the trick with this, why this was very effective, is because by including everything, you actually don't have deposit types that you say, well, we don't actually know where it fits. So this was able to is widely applicable. So that was the basis of selecting those elements. So metals, yeah, they're not going to work for the 20 intrusive complexes that we also wanted. Yeah, so it was a bit of trial and error. It was just a lot of 5 of us sitting around afternoon. There's no students involved. We're all profs and research scientists, so we just sit down and think about what we thought, what elements would work. And when you ran the DPA, they did work. But a bit of trial and error.
Can I ask a question?
Share the mic.
Well, yeah.
You can ask yourself.
I'm just wondering, yeah, this is for Steve. Did you do much CL work or anything like that on the apatites? Was there much variation? Does it matter where you laser, whether you're on the edge or the center? Whatever.
Yeah, we're very aware that zonation occurs. And interestingly enough, there's optical zonation, but the zonation that we found, it was within error precision. So the zonation we found in apatite was not very chemically abundant at all. It was actually within error precision. And so with the technique, we got above that. So the difference between the composition between, say, a core and a rim in an apatite from an orogenic gold deposit that was orders of magnitude less than between the chemistry of it sitting in, say, a porphyry copper deposit. So the zonation, it didn't matter, and it was actually quite minor, less than we thought. So you didn't need CL, and that made the technique really robust, because a lot of our chemistry studies, you want to actually trace magma evolution by looking at zonation. We didn't want that. So we've included all the zonation within the chemical characteristic of that class.
I have a question for Ross. In your orogenic pyrites, Ross, there was the usual suspects, but the nickel is, to me, early on was a surprise. Where do you think the nickel is coming from in those orogenic pyrites?
Interesting question. You can either have it coming out of the mafic rocks or coming out of the sediments. Sedimentary pyrite is nickel rich. In fact, there's some sedimentary pyrite that's mined for its nickel content can get up to 1% nickel in sedimentary pyrite, and it has quite a high nickel-cobalt ratio. Whereas pyrite in mafic and ultramafic rocks tends to have a lower nickel-to-cobalt ratio. So my preference is that it's coming out of fluids moving through the sedimentary pile to pick it up. And arsenic and tellurium are probably coming out of the sedimentary rocks too. We know they're quite abundant in sediments. That's the best source for those two elements.
Question for Ross, just following up on that, Ross. So you've done a few MITS studies, haven't you, the orogenic gold pyrites. So are you you've got enough data to begin to see correlations between the massive sulfur fractionation and things like nickel-cobalt ratio?
No, we haven't.
The reason I ask is it looks to me like those isotope signals will relate back to the host rocks.
Yeah, they could well be. We haven't got enough Archean material to look at that issue, I must admit. The only where we have got coincident databases for both the sulfur isotopes and the trace elements, we find that the best correlation, and this is the S32, S34 ratio, not the other 33 and 36, is with selenium. You get a reasonable correlation between selenium and the Del S34. And when you think of it, that's probably pretty logical, because selenium is the element that is most similar to sulfur geochemically. So it's probably logical that selenium and sulfur isotope fractionation goes hand in hand, but we haven't got enough data for the MIF. We'd like to have a lot more to be able to look at that.
I've got a question for Aisha. When you look at the plots of the epidote going away from Batu Hijau, you seem to have quite a lot of potential for what may be called false negatives or false positives in the epidote. Just wondering if you can comment on how you actually deal with that, because you're ending up with an R squared of 0.74 with what actually could be considered a scattergun of data.
Okay, so first it's chlorite, just so you know. Okay, so actually the problem of what you're talking about happens a lot in epidote as well. Oh, sorry. Because the epidotes can be zoned, and so if you're taking 15 or 30 analyses from a sample, and this is why I asked the question about apatite, and you're getting quite a lot of zonation, that's kind of what you're seeing represented in that scatter. So what you can do, what I've done in my studies is, you take the geometric mean of the analyses, and it's a little bit better than an arithmetic mean, because it takes away some of the outliers or the influence of the outliers. In an ideal world, when you're actually reducing the laser data, some of those dots that you see that are high outliers might actually be inclusions that could be removed from the data. But yeah, what you're really looking at is the overall average value of the sample.
Excellent. Could you all please join and congratulate our speakers from this last session.